let's think about the derivative of e to the x. So let's say f of x is e to the x. Then what is the derivative? The limit definition says it should be f of x plus h minus f of x over h, where h is set to 0. In our context, f of x plus h means you're replacing these two x's as x plus h. So if you have this as the definition of f, then when you plug in x plus h, that's what you get, right? So this is limit h going to 0 of e to the x plus h. F of x is just e to the x, and you get something. Now we can try to carry on this calculation, but it's something that we have never done. One thing you can do is to break this up into two exponents as e to the x times e to the h minus e to the x over h. And then the reason that you can do this is because the exponential rule says if you have the same base and you multiply, the exponents add up, right? So usually the exponential rule that people use will be going this way, right? But I'm using it backwards. So I'm breaking up e to the x plus h as e to the x times e to the h. The reason I want to do that is because then I can factor the e to the x out, right? So you get e to the x times e to the h minus 1 over h, limit h going to 0. And notice that e to the x has nothing to do with h, right? So the only quantity that changes as h goes to 0 is this one. This one changes because they depend on h. This one doesn't have any dependence on h. So you can factor this out further and just ask, what is this thing really? What is this limit of e to the h minus 1 over h as h goes to 0? And we're kind of stuck. Now, that last thing, however, does have some special meaning. To explain that, let me say something here. Go back to f of x equal to e to the x. Look at the following. What is f prime of 0? Well, again, here we use the limit definition of the derivative, where you have f of 0 plus h minus f of 0 over h. And because this is really f of h, 0 plus h is h, right? So f of h, and that means you just replace x by h. So you get limit h going to 0 of e to the h minus, and then here you're plugging in 0 instead of x, so it's e to the 0th power over h. Oh, but what is e to the 0th power? Anything to 0th power is 1, right? So you have limit h going to 0 of e to the h minus 1 over h. And that is exactly what we had before. If you go back and see it, that's exactly this part, right? So the conclusion here is that we don't know what that f prime of 0 is. Well, we know that f prime of x is e to the x times limit h going to 0 of e to the h minus 1 over h, which happens to be that this part is f prime of 0. Now, then what you should do is to try out the same thing for generic powers. I mean, who said we need to differentiate only e? We might want to differentiate a to the xth power, right? So if you had this, then what's the derivative? Well, if you use the same argument, the same exact argument can be used to show that f prime of x is a to the power of x. It's the same thing, but this f prime becomes, you have this f prime of 0. So in other words, if you know the f prime of 0 for this exponential functions, then you know its derivative. That's the only thing that we have trouble with. And what's the meaning of the derivative? Well, that's the tangent line of the slope, right? So to understand this phenomena, we have to actually think about some examples. So here are two very simple exponential functions, and as I said, y prime, if you y prime for this 2 to the x would be 2 to the x times some constant, which is the slope at 0, y prime at 0. And same thing holds for this one. This one you have y prime equals to 3 to the x times y prime evaluated at 0. So in both cases, we're really interested in the slope right here, at this point right here, because that's the slope at 0. And judging from here, you should see that this blue line has steeper slope than the red curve, right? The blue graph has steeper curve than the red graph. Let's actually try to do this. So first, for 2 to the x, we're trying to do limit of h going to 0, 2 to the h minus 1 over h. That's exactly what we had, except that we were doing it for e, but we're doing it for 2 right now. So it's 2 to the h minus 1. And because we don't have any means to calculate this, we'll just do this numerically. So we'll just plug this into a calculator. Let's see, calculator here. And I'm going to just set h to be like 0.001. That's pretty close to 0, right? So we're going to do 2 to the power of 0.001, and that's what you have, right? That's what you have. And then you subtract 1, and this entire thing has to be divided by 0.001, which is 0.6933. Okay, so this is what we got. We got 0.6933. It's somewhat like this, and that's not like any kind of repeating decimals or any integers. It's nothing like what we know, so it's kind of not so satisfactory to have that. Let's do the same thing for 3 to the x. Let's see what happens. This time we're going to do limit h going to 0 of 3 to the x minus 1 over h, not 3 to the x, 3 to the h minus 1 over h. Again, we use the calculator. All we have to change is this 3, right? Put that as 3. And it's 1.099. Okay. So this is about 1.099. Okay. And that's when we actually turn the table. We change the name of the game. And we do the following. So far, we were doing this. Whenever we were being asked what the derivative is, we plugged it into the limit definition, calculated the limit, and we got some function out of it. But that strategy is not working here because you get all these weird numbers. So why not change it so that we come up with a new value? So here is what we do. We're going to define e as the number which e to the h minus 1 over h as limit h goes to 0 gives you 1. Okay? Now if you recall, the first time you've seen e was when you were doing this in pre-calculus or algebra 2, where you learned bank interest rates, right? When you did the continuous compounding, you saw this e, and you're really not told where this e came from. It just appeared out of nowhere, right? So really, we were using e, but we were never given any reason to to why we would want to use such a strange number. This is called a natural number, but what's so natural about it, right? E is also called Euler number or Euler natural number. E is also called natural number, but why natural, right? And the name natural comes from here. E would be something between these two. It's between 2 to 3. It's closer to 3 because 3 is pretty close to 1, right? 3 gives you this derivative pretty close to 1. So I want something that's pretty close to 3 whose slope at 0 is 1. That's actually the definition that you were never given. So with that definition, here's what we have. See this green line here? It's so similar to blue, it's hard to distinguish. But this one right here is our y equals to e to the x. The actual value of e is 2.718281, and then so on and so on. Okay, so as you can see, it's bigger than 2, less than 3, but it's closer to 3, right? And for this value, this is the value that mathematicians calculated so that the limit of h goes to 0 of e to the h minus 1 over h becomes 1. And with this, because we had all kinds of derivative formulas that said if you had f of x equals to some a to the power of x, f prime of x is a to the x times f prime of 0, right? And for the special case e to the x prime happens to be e to the x times f prime, the slope at 0, but for this green line the slope is exactly 1. Exactly 1. So this slope for the green curve is exactly 1. So you get e to the x. And the result is like the simplest derivative formula there is. It's awesome because e to the x, what's the derivative? It's just e to the x. Very simple, right? Now, to figure out the derivative for any a to the x, you need to learn something called the chain rule. But let me still throw this out here. If you have a to the x and you differentiate, as I said, it's a to the x times some number. Now, it turns out that once you define it like this, and if you accept something called the chain rule, which we'll figure out later, we're going to see that this f prime of 0 ends up being the ln of a, where ln is the log with base e, right? So what I'm trying to say here is the conclusion here, so maybe I should say conclusion, is that if you have e to the x prime, that's just e to the x. If you have 2 to the x prime, that's just 2 to the x ln of 2. If you have 3 to the x prime, that would be 3 to the x ln of whatever this number is. So in general, a to the x prime would be a to the x ln of a.